In this lecture, we will discuss the nature of the singularity of the function. Now, for example, I take the first function f of z, so which is equal to 1 by sine of z minus cos of z. So this is my first functions. Now, singularity या poles of function can be obtained by putting the denominator equal to 0. So, pole are determined by sine of z minus cos of z is equal to 0. So, it implies tan of z is equal to 0. Now, this values. If tan of z is equal to 0, so z can be written as n pi plus pi by 4, where n is equal to 0, plus minus 1, plus minus 2, and so on. So there are infinite many terms. So all of these are simple pole. So these are the simple pole, the pole of order 1. Similarly, z equal to pi by 4 when n is equal to 0. So it is a simple pole. So it has a infinite number of singularities which are of this kind, n pi plus pi by 4, and it has pole of order 1, so it is called as a simple pole. Now, question number 2. It was a question number 1. So I take example f of z, which is equal to 1 over z into 1 minus z square. So just one over z into 1 minus z square. So my aim is to find the singularity of this function. So singularity of fz, singularity of function fz is given by taking denominator equal to 0. So we get 3 roots z is equal to 0, minus 1 and plus 1 of order 1. So it means it is a simple pole. So it means z equal to 0, minus 1 and 1. These are simple pole of function fz. So in this way, we can find the pole, the singularity of the function. Now, my next question is, if function is z over, so in the next function is c, and function is fz, which is equal to 1 over 1 z over 1 plus z raised to power 4. So this is my next question. So in the next question, the function is f of z, which is equal to z over 1 plus z raised to power 4. Now again on similar line of action, so singularity of a function f of z is given by taking denominator is equal to 0. So this is equal to 0. So get which is equal to -1. So which is a cis pi. So also this can be written as e raised to power -1. So this is a cis pi, and adding to n pi. So this is equal to cis of 2n pi plus pi. So which is a n belongs to integer. So what is z? So z is cis of 2n plus 1 into pi raised to power 1 by 4, where n is equal to 0, 1, 2 and 3, because it has 4 roots. So what are the 4 roots? So this can be written as z, which is equal to cis of 2n plus 1 into pi by 4, where n is equal to 0, 1, 2 and 3. So by substituting the value of n, so I get the 4 root. So this cis can be written as e raised to power iota 2n plus 1 pi by 4. This is values. When n equal to 0, so this is a e raised to power iota pi by 4, 1 root. Three iota pi by 4 when n is equal to 2. So e raised to power 5 pi by 4 iota, and then e raised to power 7 pi by 4 iota. So this is a 4 roots, and each of them has order 1. So it is a simple pole. So all of these are which are simple pole of order 1. So this is a simple pole of order 1. Now in this way we can find the singularity of the our question. Now next is, if I am taking the function f of z, which is equal to sine of z over z minus pi raised to power 2. Now singularity of function fz are given by z minus pi raised to power 2 equal to 0. So it means z is equal to pi and pi. So repeated root of order 2. If it is a repeated root of order 2, so it implies z is equal to pi is a pole of order 2. So this is a pole of order 2. So in this way, we can find the singularity of the given functions. Now after that, we will discuss some question. The statement of the question is locate the name and singularity of the given function. So next is locate and and name of singularity of a function f of z, which is equal to z raised to power 8 plus z raised to power 4 plus 2 over z minus 1 raised to power 3, 3z plus 2 raised to power 2. So this is my question. Now solution. So pole or singularities. So pole of given function fz, these are given by z minus 1 raised to power 3, 3z plus 2 raised to power 2, which is equal to 0. So it implies z is equal to 1, which is a pole of order 3 and z is equal to minus 2 by 3, so which is a pole of order 2. So this is a nature of singular point. So in this way we can find the value of this. Now after that we will discuss some more results. So which is a, for example, a function fz which is equal to, this is very important function, cot of z over z raised to power 4. So this can be written as cos z over z raised to power 4 sine of z. Now pole or singularity of this function. So pole of fz, this function, are given by z4 sine of z, which is equal to 0. So we get z4 equal to 0 sin z is equal to 0. So it implies from this z is equal to 0, 0, 0 and 0. It has 4 values. From this z is equal to n pi, where n belongs to integer. So this value is 0 plus minus pi plus minus 2 pi plus minus 3 pi. So here we have 4 value of 0 and here we have 1 value. So total root of denominator is equal to 5. So it means z equal to 0, which is a pole of order 5. So it is not a pole of order 4. So it is a pole of order 5 because z equal to 0 is also root of sine of z. So it means it is a pole of order 5. Now the other values plus minus pi, plus minus 2 pi, plus minus 3 pi, all of these are simple pole, the pole of order 1. So z is equal to plus minus pi, plus minus 2 pi, plus minus 3 pi and so on. These are pole of order 1. Also we can say that it is a simple pole. So pole of order 1 is also called a simple pole. So this is my result of this question. After that, I will discuss another question. The statement of that question is f of z, which is equal to this values 1 by z cube into 2 minus cos of z. This values. Now again, pole of fz, poles of fz are given by z cube into 2 minus cos z, which is equal to 0. So it implies z cube equal to 0 and 2 minus cos z equal to 0. So it implies z is equal to 0 is a pole of order 3. Now, how many roots of this equation? Now check that. Since we know that the modulus of sine of z is always less than equal to 1. If it less than equal to 1, so it lies between minus 1 and 1. If it lies between cos z and sin z less than equal to 1, so it means this equation has no root because it does not, because this value lies between minus 1 and 2, so this total term is not equal to 0. So z equal to 0 is the only root, so it is the pole of order 3. So it has no root, no root. So it has no root, it means it has only z equal to 0, pole of order 3. So in this way we can check that the singularity of the given function. Now next definition is, which is very important, so which is called residue. Residues at a pole. So which is residue at a pole. Residue at a pole. Now suppose a single valued function. Suppose a single valued function f of z has a pole of order m, pole of order m at point z equal to z0. It means by Laurent expansion, this fz can be written as summation of an z minus z naught raised to power n is running from 0 to infinity, plus b1 bata z minus z naught, b2 over z minus z naught raised to power 2, since it is a pole of order m. So this will be up to z minus z naught raised to power m. So this is a of this kind. So where an is equal to 1 by 2 pi iota, so f of z into dz, z minus z naught raised to power n plus 1, and bn is equal to 1 by 2 pi iota around integration c fz dz over z minus z naught raised to power minus n plus 1. So what is C? C is a circle which lies in the annual region, which is z minus z naught, which is equal to rho. So its radius is rho. Now clearly from this, check that from this, what is B1? So what is B1? Substitute n equal to 1. So which is equal to 2 pi iota integration of C fz into dz over z minus z naught raised to power minus 1 plus 1. So this is 1. So what we get? So we get integration of fz into dz around C, which is equal to 2 pi iota into B1. So this values 2 pi iota into B1. So what is B1? B1 is called a residue of a function. So what is B1? B1 is called residue of a function fz at a point z equal to z naught. So this is a residue of a function fz at a point z equal to z naught. Also, what is B1? It is a coefficient of 1 over z minus z naught in Laurent expansion of a fz. Expansion of a fz. So in this way, we can find the residue of a function. So similarly, what is the residue? It is at the point pole. It is at the point 0 या finite numbers. So how we will find the residue at infinity? So what is residue at infinity? At infinity. So remember this formula, residue at the point infinity. So what is residue? Residue of function fz at the point infinity. So what is this? So this is a minus 1 by 2 pi iota around integration fz into dz around c. So this value. So remember that the residue at the point pole, which is 1 by 2 pi iota integration fz dz, but at the power infinity it is a minus sign. So it is a negative of the values. So remember this formula, residue of fz at the point of infinity. Now for example, if I take a function f of z, so what is this? Which is equal to z raised to power 2 plus 2z plus 7 into e raised to power z over z minus 5 raised to power 2, z minus 2 raised to power 7, z minus 9 raised to power 3. So this is my function. Now here we have 3 poles. One is 5, 2 and 9. So z is equal to 5. What is this? It is a pole of order 2, right? So see clearly, z is equal to 2, which is a pole of order 7. Z is equal to 9, so which is a pole of order 3. So this is a pole of order 7, this is pole of order 2, this is a pole of order 7 and this is a pole of order 3. So this function has pole of order 2, 7 and 3. So in this way we can find the value of pole. So this is a pole of the values. So how we will find the residue? So residue, one is a working method and second we discuss, that is a definition. So what is the working method to find the pole of a order 2 या pole of order 7, pole of order 3? So how we will find the residue of any pole? Now working rule. So remember that residue of a function fz at z is equal to z naught. So this is a residue of a function. So in case of a simple pole, so simply it is a limit z approaches z naught, z minus z naught into f of z. So this is a in case of a simple pole. So for a simple pole, we can find the residue in this way. It is a one way. Second way is to write in the series expansion, then taking the coefficient of 1 over z minus z naught. 1 over z minus z naught, coefficient of that. So this is a simple pole. So it is for a simple pole. Now if Fz is a pole of order m, suppose now if f of z, if f of z, it is a some function and z is equal to z naught, which is a pole of function fz of order m, order m. So it is a for simple pole. Now we are discussing the residue of a pole of order m. Now write fz in this way: phi of z over z minus z naught raised to power m. So this in this way. So this is a pole of order m. So I write fz in this way. If I write this way, so what is a residue of function fz at point z is equal to z naught at point z naught, which is equal to 1 by m minus 1 factorial into m minus 1th derivative of this function at the point z naught. So this is a residue of a function of pole of order m. So this can also be written as, so residue of function fz at z equal to z naught, if it is a pole of order m. So this is basically m minus 1th derivative at the point z naught over square root of m minus 1 over factorial of m minus 1 factorial. So this is a pole of order m. Also this can be written as, 1 by m minus 1 factorial. So what is this? It is a m minus 1th derivative with respect to m minus 1 z. So what is here function? So here function is simply z minus z naught raised to power m into fz. So here I can write it in this way. So in this way I can also find the residue of a function. So this is a working method of a residue. It is a working method of to find a residue of a simple pole as well as pole of order m. If I would like to find the residue at the point of infinity, so what is that way? So that way is simple residue of function fz at the point of infinity. So this is infinity, which is equal to limit of z approaches infinity. Simply write minus z into fz. So this value, if this limit exists. So if this limit exists, so this is the way to find the residue at infinity, right? So in this way we can find the residue at infinity. And second way is, which is a minus time coefficient of coefficient of 1 by z. Now not a 1 by z in expansion of it is minus time coefficient of 1 by z in expansion of fz in the neighborhood of z equal to infinity. So in the neighborhood of z equal to infinity. So it is a minus time. Here it is minus and here it is a minus. So remember residue at the point of infinity, right? So we will understand more accurately by discussing the example. Now first I will take some simple pole to find the residue. Now for example, if I have a function tan of z, sine of z and cot of z, in that case how we can find a residue? If I have, it is some another method, phi of z over suppose psi of z. So this is a sum function and it has a simple pole. It has simple pole. Simple pole mean pole of order 1. It has simple pole at the point z is equal to z naught at this point. Then we can find it as residue of function fz at the point z naught, which is equal to phi. So simply substitute at this point the value of z naught over psi dash its derivative at z naught. So this is possible if this derivative is non-zero. If this psi z is not factorized, so this is possible where psi of z is not factorized. So this is a special case of raised formula. For example, so it is applicable to tan of z as well as cot of z. So what is fz? So this is a tan of z. So this is equal to sine of z over cos of z. Now from this, what we get similarly in case of cot of z. So if I take cot of z, so in that case, this can be written as cos of z over sine of z. So what is the pole of this values? So z is equal to n pi, which is a simple pole of function fz. Now how we will find the residue? So residue of fz at point n pi, which is a phi z. So ਜਿਹੜਾ cos of z ਉਦਾਂ ਦਾ ਉਦਾਂ ਹੀ ਰਹੇਗਾ, cos of z. So cos of z ਨੀਚੇ sin of z. So ਇਹਦਾ ਅਸੀਂ ਡੈਰੀਵੇਟਿਵ ਲਵਾਂਗੇ. So ਇਹਦਾ ਡੈਰੀਵੇਟਿਵ ਆ ਗਿਆ minus cos of z. So then we will substitute the value of z, which is n pi. So if this is treated as phi z, so this is treated as psi z. So its value will be phi z over psi dash z. और z क्या है? n pi. Here it is n pi. So this value will be cos n pi. Again it is minus cos n pi. So this value is equal to minus 1, right? So in this way we can find the residue of a this function. So if it look like a complicated, so just I will find the residue at the point of 0. So what is the residue of a function at the point 0? So what is this? This is a cos 0 over minus cos 0, which is equal to minus 1. So this is my result. So in this way we can use this method to find the residue of a tan theta and cot theta. Now in the next question, the statement is find the residue of a function f of z, which is equal to z raised to power 3 over z minus 1 raised to power 4, z minus 2 and z minus 3. So here these are the simple pole, but is a pole of order 1. Now, so we will discuss this example. Now z is equal to 2, 3. These are simple pole of fz, simple pole of fz. So we find it in very simple way. So how we will find? So first I take residue of function fz at the point z equal to 2. So what is this? This is a limit z approaches 2. Now multiply by z minus 2. So remaining part is z cube over z minus 1 raised to power 4 into z minus 3. This value. So this value is, which is equal to 8 over 1 raised to power 4 into minus 1. So this is a minus 8. So we find the residue of this function. Now similarly, residue of a function fz at z equal to 3. So this is limit z approaches 3. Now remaining part, so removing the z minus 3 term, so remaining part z cube over z minus 1 raised to power 4 and z minus 2. Now substituting the value of this, so this is 3 raised to power 3, so 27, 3 minus 1, so 2 raised to power 4 into 3 minus 2, which is 1. So this is a 27 or 2 दूनी 4 दूनी 8 दूनी 16. So this is a 16. So this is a residue of a function at the point z equal to 3, and this is a residue of a function z equal to 2. Now in third case, so what is the third case? Third case is z is equal to 1, z is equal to 1. So it is a pole of order 4. This is pole of order 4. So how we will find the residue? So residue of a function at the point z is equal to 1. Now here m is 4. So 1 by 3 factorial, number 1. So third derivative with respect to third derivative. So remaining part is z raised to power 3 over z minus 2 into z minus 3. Now differentiate this function up to third derivative, first, second and third, then substitute the value of, limit of z approaches to 1, then substitute the value of 1, z equal to 1. So in this way we can find the residue of the function at this point. So taking third derivative, then we will find the residue of a function at this point. So simplify, it may be 101 by 16. So it may be 101 by 16. So in this way we can find the residue of a simple pole and pole of order 1, 2 and 3 and pole of order m. So in this way I can find the residue.